We're going to practice calculating a system's center of mass, but this time with a continuous distribution of matter. So imagine that we're given a solid cylinder that looks something like this. Solid just means the opposite of hollow, namely that there's material inside the cylinder. Its mass is big M, its radius is big R, and its length is big L. The equation for the center of mass position tells us that RCM equals 1 over the total mass times the integral of the position vector times dm. So we're going to have to figure out how to do that integral. Now in this case, I'm going to assume that things are symmetric up, down, and into and out of the screen, so that really we're only interested in the x direction. So let's just figure out the x position of the center of mass. That simplifies this equation a little bit so that we're not dealing with vectors anymore. xcm equals 1 over the total mass times the integral of x dm. So the challenge here is to figure out what the expression for the differential mass element dm is. Let's highlight a region inside this solid cylinder, namely this little section right here. It has a width that I'll call dx, meaning that really we're imagining this becomes infinitesimally thin, and it has an area of pi r squared on the side, right? That's just the area of the circle. The volume of this blue section is therefore dx times pi r squared. Now to relate that to the differential mass element, we need to introduce a new physical quantity called the density. If you've ever taken chemistry or even high school physics, you may have encountered density. Density, given the symbol ρ, is a measure of a system's mass per unit volume. So if we're trying to relate all of the quantities we have to the differential mass dm, well, it should be the case that dm equals ρ times this differential volume dx pi r squared. In other words, dm equals ρ pi r squared dx. That will be the expression that allows us to solve this integral because it relates dm to dx and ρ. Alright, let's do some sample problems to convince you that this works. So first, let's start with the expression for the x position of the center of mass. And we have our expression for dm, so let's just substitute that in. And now we can pull out everything that we know to be constant. Pi r squared is certainly constant. The cylinder's not changing radius, pi never changes. So now we have this expression, and you know what? This is a useful enough general expression for a solid cylinder that I'm actually going to put that over on the left and highlight it in red. Now what we can do is go through and make different assumptions about the cylinder's density and see what different answers we get for the position of the center of mass. So the first assumption, the simplest one, is just that the density is spatially constant all the way through the cylinder, namely that ρ equals some constant ρ0. Well, if we insert that into our expression for xcm, that means that we can pull the density out of the integral, right? Because now it's just a constant ρ0, so let's do that. And we end up with this expression, so a bunch of constants out front times the integral from 0 to L, x dx. Just to be clear, if we set up the integral this way, that means that we're measuring the position of the center of mass from the left side of the cylinder, x equals 0. Okay? Well, I can do that integral. That's just going to be x squared over 2 evaluated between 0 and L. So in other words, L squared over 2. So we substitute that in. Now we can simplify this expression considerably if we realize that the total mass big M is just the integral from 0 to L of dm. So we substitute in our expression for dm, using ρ0, that means that we can pull out all of those constants and we'll just have the integral from 0 to L of dx, which is just L. So the total mass is ρ0 pi r squared L. Now we can substitute this in where we have 1 over m over here, and so that'll become xcm equals, complicated mess, it's 1 over ρ0 pi r squared L times pi r squared ρ0 times the quantity L squared over 2. Well, a lot of these things are going to cancel, right? ρ0 pi r squared will cancel, 1 power of L cancels, so that means that it reduces to xcm equals L over 2. And of course it does. If the cylinder has uniform density, we would expect the center of mass to be located halfway through the cylinder. This demonstrates that, right? xcm equals its length divided by 2. Okay, that one we could have guessed. We didn't need to do any integrals, but at least it shows you that our expression for the differential mass element seems to work. Now let's apply this same strategy to a cylinder whose density is varying spatially. So imagine that we're told the density of the cylinder is actually a function ρ0 times the quantity 1 plus x over L. So clearly the density has a minimum value, ρ0, on the far left part of the cylinder, x equals 0. Its maximum is at the far right part of the cylinder, where its density there would be 2 ρ0. So the density varies. Now we have to do the integral, and now you can't easily guess where the center of mass is, although we would guess that it's probably located to the right of center, right? It should be greater than L over 2, given that the normal density profile is right in the middle. So the first step is just to substitute this density into our expression for xcm, just like we did last time. The difference is now we can only pull out a ρ0 but we have a more complicated integrand, right? The integrand now is x times the quantity, 1 plus x over L dx. So let's separate that into two integrals. Both of them are pretty easy, you just need to do the bookkeeping carefully. So first integral becomes L squared over 2. Second one is 1 over L times the quantity L cubed over 3. We can find a common denominator there after we cancel out a power of L. Common denominator will be 6, so we get that xcm equals 1 over m pi r squared rho naught 5/6 times L squared. So that's a different expression than we had before. But of course, we also expect that the expression for big M will be different, right? We have a different mass profile, so we need to recalculate that. We can't just use the same expression we had before. So big M is still the integral from 0 to L dm, but now when we substitute in our expression for dm and insert the density profile, you'll see that we can pull out rho pi r squared, but now, again, we have a different integrand. So now we have to integrate this. So we separate this into two integrals. We do the two integrals and find that m equals rho pi r squared times 3/2 L. So that's a different expression for big M, just as we have a different expression for xcm. Now we can combine the two, and we do it in exactly the same way as before. This expression gets inserted in where we have a 1 over m up here. So we do that, and again, a bunch of stuff is going to cancel. So rho pi r squared will again cancel. 1 power of L will again cancel, because we end up with 5L squared over 6 times 2 over 3L. Power of L cancels. So we get that the x position of the center of mass is 10/18 L or 5/9 L. I would not have been able to guess that without doing some integrals, and you can see that it matches with our expectations though, namely that 5/9 L is greater than 1/2 L. So the center of mass has moved slightly to the right, but not that far. If we had a more extreme density profile, one that varied more dramatically, you might imagine that the center of mass would move even farther to the right, but for this case, the center of mass is now located at 5/9 times the length of the cylinder.